take the edge off all those struggles you may have for using calculus. So let's go ahead and go forward here. We're going to talk about limits using graphs and tables. So the whole intuitive idea of a limit, you're probably just learning just what it is. We're going to assume that f of x is defined for all x, just getting all the technicalities out of the way. And this is what a limit looks like. That limit, we say to read this as a limit of f of x as x approaches c is equal to L. All limit is just an approximation of height. It depends on the path. So it's like we're walking down a path as we get to it. So let's just pretend we're walking to our house, or as you're walking to your house, that's the path we're taking. And where is your house located? Pretty much all that is. So we're going to focus this on height. Okay, and you'll kind of see that as I do some drawings within some of the graphs. Relationships that we do need to be aware of is that the limit will exist only if the left path and the right path are equivalent. So for this problem right down here, we're going to use a table to see a result and estimate the limit as x approaches 0 of sine of 2x over x. What we want to do here is, here's a table. Like I said, we're walking to our house, but it's a little foggy out. We can't see it. So we look at our x's. We know that we do want to get closer and closer to this value right here. So as we're walking to our house from the left, what is the location of our house? And we're just looking for height only. Well, we're getting closer. We're at negative 1.1. We're at 1.986. Then we get to negative 0.01. That's super close to our house at 0.99986. And then we're even closer to our house. So you can estimate that our house is going to be located at a height of 2. Now, if we take a walk on the other path from the right, you can see that the same thing is going to happen here, and we're getting closer and closer to 2. Since both paths are matching, we're going to equal this to 2. All right? So pretty much what's going on right here is a little stick figure guy. This is as good as my drawing gets. This person is walking. This is the graph of that function. Is walking and walking, and then we don't want to know exactly where that person is standing, but we want to see on this path as they're walking to our x value, where are they going to be about? Okay, all we're doing is approximating. So let's use that same idea here to find the following limits. So we have the limit as x approaches 1 of h of x. H of x is this piecewise function right here. Lots of stuff going on, lots of holes, a couple of dots out of nowhere. So let's talk about the meaning of limits as we go through this. So for that first question, we have the limit as x approaches 1 of h of x. So we are going to be walking along this path right here from the left. And if you notice, we are getting closer and closer to a height that's just above 2. As we're walking on this path on over here, from the right, we are getting closer and closer to a height that's just above 2. Now, I do not want you thinking it's the exact value, because the exact value at 1 is 3. We can tell that by looking. But I don't want the exact value, I want the approximation. So as we're walking, getting closer to x, what height are we before we actually get to our house? What height are we right here? Like I said, we're a little above 2. Let's just call that 2.25. We're just estimating right now, not looking for exact answers, unless we can give an exact answer. For the second one here, what's the limit as we approach 2? So let's talk about approaching our house here. So as we approach to find our house on the left-hand side, we're approaching a height of 3 as we are walking. I'll even draw a little stick figure here, walking, okay? Now, if you're walking on that path, let's say that your brother and sister is walking on this path trying to get to this location, are you two going to match up? The answer is no. Since the two paths do not match up, this answer does not exist. That's what D&E stands for, does not exist. And anytime we put does not exist, we have to explain why. That is the limit as x approaches 2 from the left of h of x, which is 3, does not equal the limit as x approaches to the right of h of x, and that is 1. Since those paths are not equal, we do not exist, and that is from our relationship between one-sided and two-sided limits. Okay, so now this walking to our house thing, this just took a whole new turn right here. So composition functions are a lot different. We're still going to walk to a building that we don't know where it is on a map, and we're going to do our best to estimate where this building is. So as we are walking to our path here for h of x, it's important to know for all composition functions, that's when functions are embedded into other functions, is that composition functions don't actually look like the functions that you see right here. They look a little hidden, and I'm going to get into that part in just a second. So we're first going to approach 4 as we get to h of x. So as we're on this path walking to get to 4, our height is approaching 2. Now, for composition functions, it's important. Are we approaching the height from underneath 2 or from above 2? So since we're going uphill, you can tell from my person walking right there, we are going uphill. If we are looking at the limit as x approaches 4 on my left path of h of x, of h of x, because this is a composition, I need to write this as another limit. This is equivalent to the limit as x approaches 2 to the left, because we are smaller than 2 because we're walking uphill here of h of x. And now since we're on this path, we're going back to, the red guy right over here. I will circle that. That path right there is approaching 3. Now, as your sibling is going through that same path, that's the limit as x approaches 4 to the right of h of x. H of h of x. They're also approaching the x value of 4, but from lower. They're underneath 2. So because they're approaching and they're going uphill, they're always under 2. So we have to rewrite our composition limit as x approaches to the left. And this is going to give an answer of equivalently 3. So this limit right here is equal to 3. So let me go ahead, and for those of you that are like, that's not right, I'm going to go over here and look at Desmos. And I have written out this function right here to look pretty close to what we have here for our function, and just to kind of let you know that Desmos doesn't show the jump here, but you can see that there is a 1, 3. It doesn't show it unless I'm hovering over it. So if I were to take h of x, which is this blue one right there, that blue and that red look different because, like I said, when we do composition of functions of themselves, they turn into new functions. So now I'm on blue, and you can clearly see that as we're approaching 4, we are reaching 3 of this composition function. Let's go to the limit as x approaches -1 of h of x. This one is, if you thought everything else was hunky-dory, it might change right here. So for this one, we have no rate of change, ROC, rate of change. Every other path we've been walking up, we've been walking down. This one has absolutely no change, which is a big deal for a composition function only. Because there is no change, the path is constantly the same thing. So this means that our height is going to be the same at -1 because it is a composition function. So actually, sorry, not -1. I'm looking at -1, at +1, because my height right here is +1. So I'm looking at h of +1. And h of 1 is equal to 3. In case you're getting a little sketched out by this, let's go ahead and look back at our blue function. So as we look at -1 right here, we can clearly see that our height is 3. If you notice, this entire constant part of our red for this composition function, because it is constant, all it does is gets composed onto blue, which is also constant. We just got to find the height of that blue, which is the h of x. And it all happened because we are at 1, 3 right there. Okay. So now let's look at our last 2 examples here. And these are examples of the limits that do not exist for different reasons. So first we have the limit as x approaches 0 of cosine of pi over x. And you can notice on these paths, if you're walking on these paths right here, get off the path, because you're going up and down, and you can keep going up and down, up and down, up and down. So because of that, we're going to keep, it's called oscillating. So we will never reach a destination. This does not exist. Let me explain why. Because cosine of pi over x oscillates. I can't even spell oscillates. As we approach x equals 0. And then for this last one right here, this is an absolute value divided by a non-absolute value function. That's the same thing. And you get the function that looks like this right here. So we can clearly tell that this path on the left and the right do not match. So this will be a does not exist. Hopefully you caught that before I even wrote it. So limit as x approaches -1 of the left, absolute value of x plus 1 all over x plus 1, which, by the way, is -1, does not equal the limit as x approaches -1 from the right. And that will be a height of 1, and that is going to wrap up our video here. Do not forget to like and subscribe.